Okay, so today we're going to learn about or review families of functions. Okay, what that means is there's different types of functions, and we try to find ways to identify each type based on a graph, based on a table, or based on a scenario. So here are the three functions that we have reviewed this year. We're going to go over each one of them separately, starting with the linear. So the linear family. So the linear family, on the graph, just a linear equation. The graph of a linear function is just a straight line. That's all that it looks like, just a straight line. It could go this way or this way. But if it's a straight line, then it is a linear function. Okay. Then we have the table of a linear function. So the table of a linear function adds or subtracts the same amount each time. So, for example, let's take this first table here. We see that the x values are going by ones, which is good. It's constant. It's going by 1. And then if we take a look at the y or the f of x column, the way that it is increasing is by adding 2. Right? So we can check that. -3 plus 2 gives us -1. -1 plus 2 gives us 1. 1 plus 2 gives us 3. 3 plus 2 gives us 5. That's how we check that this is a linear function. Let's take a look. For example, this one. This one, it looks like it's decreasing. But let's see if it's decreasing at a constant rate. First, let's take a look at the x values. The x values, they're not going by ones, but they are going by 2s, it looks like. So it's still constant. We're still just adding 2. So that's okay. Now, the t of x, or the y column, it is decreasing, and it looks like it is decreasing by, so it's subtracting 2.5. Subtracting 2.5. And we can check that, right? 10 minus 2.5 gives us 7.5. 7.5 minus 2.5 gives us 5. 5 minus 2.5 gives us 2.5. And 2.5 minus 2.5 gives us 0. So since we are subtracting by a constant value, this is also a linear. Since we're adding by a constant value, this is a linear. So that's how you're able to tell if the table is a linear function. Okay, so we just went over the graph of a linear function. Looks like a straight line. The table of a linear function looks like this, where the values are being added or subtracted by a constant number. Okay, so, and then I'm just going to ask you to annotate that to make sure that whenever we think of linear, these are the operations that we're thinking about. Because now we're going to talk about the exponential family. So the graph of an exponential function looks like a curve. So if you see, we have a curve here. It's going like this. An exponential function can also be a curve going down this way. But notice it's not a straight line. It's not a straight line like a linear, and it's not a U like a quadratic. And we'll talk about quadratic in a little. But the exponential family, the function is a curve, like the star of a roller coaster. Then when it comes to our tables for exponential function, I want you to please annotate that the operation that we're doing is multiply. So we're pretty much multiplying the f of x value, or the output, or the y value, by 2. So we're multiplying, and this time I'm going to use that for multiplication. We usually don't, but times 2 times 2, right? So 2 times 2 gives us 4. 4 times 2 gives us 8. 8 times 2 gives us 16. Okay, so we can tell that this is an exponential function because we're multiplying by the same value. Okay, and I also want to mention that we could multiply by a fraction, and that would make something, or decimal, and that would make these values go down. But as long as we're multiplying, we are doing an exponential function in the table. Okay. All right. Now I'm going to talk about the quadratic very quickly because we're going to do quadratics in a different unit, but I wanted to show you guys what the quadratic looks like. So we've talked about this. A quadratic function is a parabola, and it looks like a frowning face or a happy face. Okay, so we're going to talk about all those when we do quadratics in a later unit. But I also wanted to talk about the table of a quadratic. And if you remember when we were doing quadratic, we always identified our vertex. Some of us identified as like the middle point because everything on the opposite sides of our vertex was like a mirror, right? So I can bet that after this would be 3. So, but we're not going to focus too much about this quadratic table or graph because we're going to do that in a different unit, in a different video. Okay. So at this point, if you would like to pause, rewind to go see what linears are again, linear function tables and linear function graphs, comparison to exponential function tables and exponential function graphs, you can do that. And then we're going to go ahead and talk a little bit about we're going to actually do a sample regions question. Okay, so the question reads, Rachel and Mark were given the information shown below about the bacteria growing in a petri dish in their biology class. So this time the table is horizontal, but it's okay because we still know that the top row is X and the bottom row is the output, B of X, or otherwise known as the Y. Okay, so now it says Rachel wants to model this information with a linear. So Rachel believes that this is a linear. Mark wants to use an exponential function. Which model is the better choice? Explain why you chose this model. So we got to see if we're agreeing with Rachel, who says that this is a linear, or if we're agreeing with Mark, who says that this is exponential. Okay. If we look at our X values, it's all going by ones. So that's great that it's constant. So we don't have to do much analysis there. Let's focus on the B of X, or our output, or our Y row. So one way to know if these numbers are being added or they're being multiplied is to kind of find the difference between them, right? So we can start out, I usually actually always start from like the end and then work backwards, because what we're actually going to do is first let's try if this is a linear. Let's try to find the difference between each step, okay? And if we get the same difference, then that means it's a linear. So let's start with 1,680, and in my calculator, I am subtracting that minus the one right before it. So 1,340. And the difference is 340. Okay. Now let's subtract and let's find the difference between this one and this one, right? So I'm going to subtract 1,340 minus 1,070. And that actually gives me 270. So right there, I can tell that this is not a linear, okay? Because to go from, now let's not work backwards. Now let's double check going the, the normal way. So to go from 1,070 to 1,340, we had to add 270, right? And then to go from 1,340 to 1,680, we had to add 340. That means that we're not adding the same thing. So immediately we know that this is not a linear function. Okay, so let's go ahead and now, actually, if you want to pause the video and take some notes down, you certainly can do that. So now let's go ahead and see if, since we know that Rachel was not right, we can see if Mark was correct in saying that this would be an exponential function. Okay, so let's take a look. So let's erase this. And now, if you remember, we said that this is exponential if we're multiplying the same thing to get from one number to the other. Okay? So just how we kind of test it out by finding the difference, so by subtracting, we're going to test this out by dividing, but from backwards. So we're going to divide backwards, and that's how we are going to figure out whether or not this was an exponential, like Mark said. Okay, so let's start with this one. So we're going to, once again, divide 1,680, and I'm doing that in my calculator, divided by, so this time we're divided by 1,340. And we get something about like 1.25, right? Okay, now let's try 1,340 divided by 1,070. So if we divide this one divided by this one, we get something that also rounds to 1.25. So let's try it again. We're doing 1,070 divided by the one before it, so that's 860. And so we get like about 1.24. The rounding in these numbers are a little off, or rather, when we round it's a little off, because we're talking about bacteria, from your bio class. Bacteria kind of grows to really big numbers, so that's okay for now. Now 800, but usually you're gonna get the exact same number. So now we're gonna divide 860 divided by 690, and we get about 1.25 again. Then we do 690 divided by 550, and again we get 1.25. And then 550 divided by divided by 440, and we get 1.25. 440 divided by 350, about 1.25 or 26. 350 divided by 280, we get 1.25. And lastly, 280 divided by 220, and it's about like 1.27. But pretty much, again, the numbers are, I rounded them, but they go like to a lot of decimal places, but they all seem to be multiplying by the same number. Now, this is where it might get confusing. We divide it backwards to figure out what we're multiplying this number by to get the next one when we're reading it in the right direction, okay? But the point is, we're multiplying each number by about 125 to get the next one, okay? So since that's the case, that we are multiplying, Mark is correct. So Mark is correct because we are multiplying each p of x value by about 1.25 to get the next one. Okay, so at the very least, we completely proved that Rachel was wrong because we were not adding the same number anywhere near close. And then we found that Mark was correct. So you can go ahead and pause the video. And then I just have one more thing to go over, and then you can get into your Regents practice. Okay. So the last thing that I want to go over is how to tell if a situation models a linear or an exponential function. And I don't know why this part is there. Gonna go ahead and erase that weird sentence that shouldn't be there. All right, so once again, the last thing that I want to go over is how to tell if a situation models a linear or an exponential function. And to do that, there's a little bit of a hint. So the hint is knowing these keywords that always tell us that we're dealing with an exponential function. So if a situation talks about doubles or triples, if it talks about a fraction of something like half or 1/3, or if it has a percentage, then that means that we're dealing with an exponential function. So for example, the attendance at a professional sports team's game decreases by 1.5% each year. The fact that it's dealing with a percentage makes this exponential. Okay, so let me actually summarize this by saying a percentage means exponential. Okay, let's look at a second scenario or situation. The number of cells in an organism doubles every 4 days. So here we have this keyword doubles. So doubles tells you right away that we're dealing with an exponential function. And the last one, the concentration of medicine in a person's body that decays by a factor of 1/3 every hour. So 1/3 is a fraction. So that means we are dealing by an exponential function. Okay? So if you have a multiple choice, it's asking you to determine which one is linear. You can eliminate any that have these keywords. Or if it's asking you for which one is exponential, you can see which one talks about this and which one includes these keywords, and that would tell you that it's exponential. So go ahead and pause the video if you need to, rewind, rewatch anything, and then get into your Regents practice.